Welcome everybody. This is Rohit. We're part of the Engineering Graduate Students Council and in association with Shah, who's from the Graduate Students Affairs Committee, for the team, and Amanda as well as Zach were also part of the GSA. We're hosting this research seminar, which is essentially an initiative for us to provide opportunities for students who are engaging in any kind of research at Columbia to present their sort of research in whatever ways they can to the larger public as well as to the incoming students and the current students. So today, especially to talk on a very niche topic, which is on sort of self-supervised learning in digital tampering detection, we have a very accomplished student who is part of the MS-cum-PhD program in the computer science department, and his name is Basile Van Hoorick. Basile, I hope I got that right. We checked with Basile a while back, and he's working with Professor Carl Vondrick, who is from the computer science department. And Basile sort of specializes in computer vision, notably in self-supervised learning, which is a form of machine learning that leverages unlabeled data to learn useful representations of the visuals of the world around us. We will get more insight into this on what essentially is the research that he is doing in this field, but just to know more about his related interests, which include perception for robotics, on computational photography. He's also into media forensics, for that matter, and he's been brilliant at what he does, which is why he's been supported by Belgian American Educational Foundation for a scholarship that is supporting his education. And at this point in time, Basile is interning at Waymo, and he's working on 3D perception, which in itself is a very cutting edge technology in the world. So prior to this, before Basile came down to Columbia, he was doing his electrical engineering at Ghent University. I hope I got that pronunciation right, in Belgium. Well, so we don't want to sort of take too much of time away from Basile, because we want to sort of listen to his interesting presentation, and he's got something really interesting to share today. So we'll hand it over to Basile, and if you have any questions, as Shad mentioned, we can field those questions towards the end, and you can always sort of ask those questions in the chat box. So over to you, Basile, and yeah, we're here to eagerly listen to what you have to share with us.
Yeah, thank you for the very grandiose introduction. So as Rohit said, I'm Basile Van Hoorick. I'm working with Professor Carl Vondrick, and I'm going to be talking about today about how lens flaws can reveal image cropping. Alternatively, how we can help fight fake or misleading news by leveraging features that are often regarded as bugs or shortcuts in the context of neural networks and representation learning. So let's jump right into it. This is the table of contents, pretty unsurprising, I would say. So we're going to talk about how to detect cropped images and why would we be interested in image cropping in the first place? Well, I'm going to give you a few motivating examples. Consider this photo of, well, is it a scary shark or is it just a duck swimming in the water? How about this one, a photo of a nice beach with some rocks? Or was there actually a person standing there and somebody tried to hide her? Next, we have this very relevant example. This actually appeared in a recent news article. We have a photo of these 4 climate activists, but as it actually turned out, there were 5 of them. So whoever wrote that news article has deliberately cropped out this African climate activist. And as you can imagine, that was quite a disastrous move. And then this is an example I literally became aware of like 1 or 2 days ago. And the recent the many Black Lives Matter protests are going on. News websites and other sources are also trying to perform kind of this soft manipulation, which means cropping images to hide certain parts. And we have, for example, this person holding a stick, for example, and BBC will kind of crop that person out. So there's a lot of things going out in the world, and a lot of manipulation is going on as well, right? And the point that I'm trying to make is every picture tells a story, and sometimes we can dramatically alter that story by cropping it, which is a very simple operation. And people say a picture is worth 1,000 words. Well, you can change those 1,000 words just by cropping, just by hiding certain parts of the image. And that is what I'm getting at. Is there a way we could have anticipated this? So can we somehow detect that this image is incomplete without necessarily having access to the full image? And this is research question number one. How do we build a deep learning-based pipeline that can distinguish cropped images from original non-cropped images, essentially? And of course, in our work, we are going to look beyond trivial details, such as the aspect ratio. Sometimes you can tell that an image has been cropped just by its weird aspect ratio, but this is not always the case. There are still a lot of degrees of freedom to crop an image in such a way that it doesn't look cropped. This could have been taken by a camera because the aspect ratio is still approximately 1.5. You wouldn't know beforehand, right? So the aspect ratio is not a reliable factor. The same thing holds for the camera make and model. We're not relying on any exit metadata whatsoever. All of these values could easily have been faked or masked. So we're going to rely on the pixels within the image only. The next question is, well, when can you actually tell whether an image has been cropped or not? What are the clues? What are the features that our model relies on? So I'm going to kick off by giving you a very short lecture on camera imaging systems. You should know that a camera is a very complex device. There's this whole pipeline of steps that occur whenever you go from a scene with the actual light waves up to the image that is being stored on your computer. So all of these building blocks are very worthy of studying themselves, but I'm going to focus today mostly on the lens, because lenses are imperfect, and the lens is going to have certain aberrations, certain flaws in it, which are going to leave fingerprints or traces behind onto the final image. And these artifacts are actually dependent on your position within the image, right? The manifestation of certain lens artifacts are going to be different on the upper left of an image as compared to the upper right of an image, for example. And let me give you a few concrete examples of what I mean. One of the most important lens aberrations that we're going to look at is called transverse chromatic aberration. This is what we know as color fringing. If we look at this small part of an image over here, in the area where the truck switches from white to black, we can see that there are these weird color bands, right? This kind of red over here, but green over here. And this is actually caused by the frequency-dependent refractive index of light. If light is coming in from the scene, then this lens will bend. The angle at which the light bends will depend on the color channel of your light, right? This will give rise to lateral chromatic aberration, but also transverse chromatic aberration. So the former means that the in-focus plane is going to be different for different color channels, depending on the frequency of the incoming light. And transverse chromatic aberration is actually the most important component here, because it means that the green point, the green light, is going to be focused at a different spatial position on your sensor as compared to the other two color channels. So this magenta is just red and blue combined. Most lenses are constructed in such a way that red and blue are aligned, but then green is kind of the culprit. So green will get focused at a different point. You can also see that this will depend on the position, on the angle of the incoming light, right? So if this incoming light were to have a different angle, then obviously the spatial offset between these 2 points is going to be different as well. All of this means that the direction of this color fringing and also the extent to which it occurs is going to indirectly reveal your position within the image. So this is an artifact that's location dependent. Right. We also have vignetting, which is a popular Instagram filter as well, but it's actually a real lens artifact. It simply means that it simply talks about the decrease in brightness as we move away from the center of the lens, as we move away from the center of the image, so to speak. And it's simply caused by the increasing angle of the incoming light means that fewer light rays will actually reach the sensor itself. And the gradient of this brightness decrease will again reveal the angle that you're making with respect to the center of the lens. We also have radial lens distortion, which simply means how a perfect square grid would get distorted either as a barrel like this or a pincushion as shown here. So with this background knowledge in mind, what are the actual tasks that I'm trying to solve here? Let's look at the following proxy task. So consider a small image patch. I could have extracted this patch from anywhere from this image. This is just a bunch of pixels, and then I'm tasking a neural network to predict the original position of this patch. All right, so I'm feeding in this small patches, which is like 96 by 96 pixels, and then I'm gonna ask the network, I'm gonna train the network to predict the position of this patch within the original image without having any access to the image itself. And so we define this normalized coordinate space. So -1 would be like on the far left or on the top of the image. And then we are trained in our network to correctly predict the pair of XY coordinates of this patch within the image space. We could, for example, predict a point that corresponds to this location, but then the true location could have been here. And then we can treat the distance d and the angle theta as evaluation metrics of our model. Now, you might have some sort of intuitive feeling where we are going with this, but how do you actually leverage this network? How do we, after training this model, how can we use it to do what we want to do, which is to reveal cropped images? And this is the answer. I'm going to design the following procedure. Imagine that you were sending me this image over a social network, the picture defined by the orange boundaries over here. What I'm going to do is this. I'm going to I'm going to extract patches all over the place. Right, so these are the teal small boxes over here. I'm going to literally scan the image and feed in every patch into this neural network that I defined previously. I'm going to obtain a set of XY predictions, and then I'm going to try to reconstruct the layout of my image according to those outputs. So for example, a patch extracted from here could get mapped to a position that corresponds to this on our reconstruction image space. And this is what we do for every patch that I'm extracting from this image. Right, so we are kind of retracing the position. We are asking the network to retrace the position of every patch relative to the center of the lens. And this is what we get. And as you might notice, something is off here, right? The predictions are actually consistently biased towards the lower right. Remember, this is the image that you sent me over Facebook, for example. I don't have access to any of the other pixels in the image. And then this is what my procedure gives me. And this visualization means that the photo that you sent me was in fact incomplete. There is a lot more content that is being hidden away behind those borders, right? And you can just tell that by looking at the missing regions. Like there are not enough patches that belong to the top or to the left of this reconstructed image space. Right, so this is how we're going to reveal cropped images. This procedure is actually automated. We're going to measure the extent, we're going to measure the amount of bias that is present in this reconstruction. And that is how we're going to make a decision, an automatic decision on whether an image is cropped, yes or no. Just to give you some more training details. So the absolute patch localization model was trained using nearly 1 million photos that are downloaded from the Flickr website, which is a website full of very high quality professional camera systems, images uploaded from those. And as you can imagine, the task itself is quite challenging because every device is unique. Every camera system is different. Every lens, in fact, is unique as well. There is a huge amount of diversity. There's a huge amount of variance among the manifestations of chromatic aberration and vignetting and other factors as well. However, since we are using a learning-based approach, we know for a fact that machine learning approaches and neural networks are in fact capable of looking for patterns, for features across the data sets, even if the task is very difficult, right? So it's simply going to try the best it can at this absolute patch localization task, even if it's kind of noisy and even if it's not very accurate. So I hope everyone understands this. It's kind of weird just talking to my laptop and not seeing any faces. But anyway, right, so let's jump to some of the results that we've achieved. If we apply the aforementioned methodology on the Flickr test set, then we can achieve a classification accuracy of 61%. And this may not look extremely high, but remember, we are kind of the first to, at least to the best of my knowledge, we are the first to build a crop detection system that works on completely unconstrained images, right? You just feed in an image, you can tell whether it's cropped or not. And also guessing, just random guessing would be like 50%. So 61% is already considerably higher, right? It will at least give you an indication or a statistical probability that an image has been tampered with. And the next series of experiments, we performed some careful investigations on the lens aberrations that I introduced previously. So remember, we had chromatic aberration and veiling as the most important factors. But what does this have to do with the model I trained? Well, it turns out that if we manually exaggerate those lens imperfections, for example, if I artificially increase the degree of color fringing, or artificially increase the degree of vignetting, which is like making the sides and the corners of the image darker, then the accuracy increases. It becomes our system becomes better at detecting crops. This means that the neural network or the ensemble of neural networks have learned to have automatically discovered those lens flaws without being ever explicitly instructed to do so. Right? We never had to create a model of this imaging pipeline. Just for the record, it says my internet connection is unstable. Can you still all hear me fine?
Basile, I can hear you. Your video has frozen up a little bit, but let's see if we can. Let's take a second.
I've moved my microphone a little closer. Is this better by any chance?
I think so. Can you say a couple more words?
Yeah, I can hear you, Basile. I think it's fine.
Okay. Yeah, so I'm going to continue. So on the other hand, we were wondering if these lens artifacts are the only factors that the network is looking for. Because we noticed that Flickr is kind of biased towards images that are taken by professional photographers. These are very often high quality photos. Most of them actually have persons in them. And again, most of them contain good looking scene compositions as well, right? You're only going to upload a photo to Flickr if it's a good looking photo, if it kind of makes sense to do so. This results in the manifestation of a so-called photographer's bias. Photographer's bias simply means that not all images are created equal, and the desire to capture meaningful content implies that some configurations, some compositions are going to be seen more often than others. For example, the sky is usually on top, and people and other interesting objects will often be intentionally centered within the image. And let me investigate this in more detail. So in order to rigorously measure the effect of photographer's bias, I captured all these photos with my smartphone, and I divided them into 5 categories. So the first class we have is upright photos, and this consists of, as the word says, a bunch of upright photos. And then we have the tilted category, which is what happens if you kind of rotate your camera into kind of angles that don't really make sense, right? You certainly wouldn't see these photos on Facebook or Flickr. And what we see is that the crop classification accuracy drops slightly from 62% to 59%. On the other hand, if we have photos with a lot of vanishing lines in them, and the Clumbekamp is actually quite perfect for this, the performance increases again to 66%. And then for heavily textured images or photos of just blank white walls, the accuracy decreases again to 57 and 55%. So what can we conclude from this? And the answer is, well, the network has not only picked up those lens imperfections that I talked about, but also photographer's bias to a small extent. So the model is relying on the fact that grass is usually on the bottom of an image, the sky is usually on top of an image, and therefore the tilted category appears to be slightly confusing the model, which explains slightly lower accuracy of our crop detection system. By the way, just to clarify, the methods of measuring the crop accuracy is simply done by randomly cropping half of all the images, which means that chance would be exactly 50%, but the network obviously performs better than chance. Here are some more qualitative illustrations. So you have this input image, again defined by the orange boundaries. I am scanning the image and I'm extracting patches, densely sampling patches from the image. Reconstructing the layout according to the absolute patch localization outputs. And this is what I get. So again, there is a clear bias among these predictions towards the upper left of the image. This means, and coupled with these missing regions, means that the image has been tampered with. It is in fact cropped, and we correctly mark it as such. Another example is if we feed in an original image that has not been cropped, we perform the patch-wise reconstruction. And of course, the result isn't perfect. Like some predictions are kind of noisy and patches will get jumped to places where they don't belong. But nevertheless, the general trends is that there are no missing regions, right? The predictions, the extent to which a deviation occurs from how an original image should behave is limited. So therefore we can mark the image as untampered. What are the takeaways that we can derive from this research and from this presentation? First of all, we are, to the best of my knowledge, the first one to leverage deep learning-based approaches with a set of unlabeled images to perform crop detection. And second of all, we've also discovered, we've also learned by a series of careful experiments that the network has automatically discovered features that correspond to chromatic aberration and vignetting, which is very interesting. On the other hand, photographer's bias, so the presence of object semantics, perspective clues, and image structure also plays a small role, which may or may not be desired depending on the application. So by kickstarting this line of research, I'm kind of hoping to join the bigger fight against fake or misleading news. It doesn't always have to be fake news, but there's a lot of misleading news out there as well, which is just like normal news website kind of trying to hide certain parts of the image in order to alter the story that they are trying to convey, depending on whatever the specific agenda of that news website is. So I really do hope that by opening an opportunity for verifying the content that we see online, hopefully we can start putting people's trust back into the fields of photojournalism and photography in general. I think cropping happens more often than we think because it's not something, I mean, it is actually not something we think about, right? But I think especially in these recent times of civil unrest, people are just manipulating images left and right. Some are using advanced photoshopping techniques. Others are using much simpler techniques, which include cropping. You can achieve, by the examples that I had shown in the beginning, you can really alter the message. You can really change the context of a picture by simply cropping it. So yeah, that concludes my presentation. So let's move on to questions now. I hope the quality was somewhat manageable. I'm on a wireless connection here. Maybe I should have connected the cable before this presentation.
I think it was fine, absolutely.
Okay.
Yeah, Basile, it's fine. So any questions? We would love to field some questions. So Basile, let me start with a question. So have you sort of created a running model with this where, you know, you sort of come up with the initial sort of prototype for it, or is there a proof of concept that you worked upon, and what have the results been like in terms of the applications?
So, I mean, it is more of a proof of concept. Again, this is still in the research phase, right? I'm hoping that future researchers will kind of build on this and improve the performance, improve the applicability of this model. This is definitely the first iteration of many to come. But I do think that there are some useful applications. One of them, one of the most obvious ones, would be to detect misleading photojournalism. I'm talking about the people who are cropping photos like this and then hiding certain persons or hiding certain items that people are holding, for example. So I think exposing misleading news is one of the applications, and the wider field of digital forensics could also benefit from this. So I hope this kind of answers your question. I believe in general, the opportunity to be able to verify that a photo has not been tampered with can really help put people's trust back in photographers in general, right? Photography is a creative field, But if people can't know for sure whether or not they should trust the content that is created by those photographers, then this kind of indirectly hurts their careers. So that is one of the applications that come to mind.
Sounds great. So I think you have a couple of more questions on the chat box. I think Vishal is asking, can the results be improved by incorporating camera info as well? And
that is a great question. And I think that is one of the possible paths that could be taken into the future. Again, I'm just one person. I can't solve every issue within a semester or within a year, but I would love to see what happens if you kind of use the camera information as part of input of the neural network. Because right now, the method is designed to work in the blind. And the benefit of that is that it doesn't need camera information. But the drawback is that it doesn't use camera information, if you kind of understand what I mean. So it's just a choice that you make. You could choose to either include or exclude it, but it would be great to be able to research the alternative as well. What if you do know the camera make and the camera model that the photo has been taken with? Can you talk more about the choice of your ML model? So I'm going to jump to this diagram. The backbone of this patch localization network actually consists of a series of classifiers on multiple levels. So given this patch, this is a sort of small patch, there's an input to all of these classifiers, and all of them will say on a particular grid where in the original image space the network thinks this patch belongs to. And then all of these predictions are averaged, and that is how we produce the yellow point estimate. I think your question more specifically is why ResNet 18? Well, because ResNet 18 is one of the fastest networks to train, right? Training machine learning model takes a lot of time. I think any instance of this model end-to-end would take like 1 or 2 or even 3 weeks, simply because the Flickr dataset is a huge dataset, and we want to be able to leverage a huge dataset in order to train as accurately as possible, in order to obtain an accurately as possible model. And the reason why I use ResNet 18 and not ResNet 34, for example, is also because the features that we are looking for are not very high level, right? So it's not like we are explicitly looking for high level object semantics. Things like chromatic aberration and vignetting can be detected by a shallow network such as ResNet 18 because the features are not extremely complicated to begin with. So, and that explains the choice of our ML model. How did you set up the border between tampered images and original images? So I think there's kind of 2 different aspects in this question. Remember that we had 2 different tasks, and only when composed together, they would constitute the crop detection method, right? I think the main question is, how do you decide whether an image has been cropped or not? Well, I am defining a cropped image as any deviation from what the original camera captured at the beginning, at the time of when the photo was shot. But of course, if the photo is cropped by just 1%, is that a crop? And to my definition, it's not. The maximum crop factor I'm considering is actually 0.9. So actually, either you have an original image, or either you have a crop in which both dimensions are like reduced by at least 10%. This is just to ensure that there is like a somewhat significant gap between tampered and untampered images, because otherwise you could go into pointless discussions about whether 98% crop actually constitutes a crop or not. So that's why I decided to pick the 90% threshold. I hope Parth Doshi, I hope that kind of answers your question. Is the tampering focused mostly on cropping and the misleading the scope of the photo, or can this pick up on photoshopping as well? So I believe that, well, you could try to incorporate investigating all other kinds of manipulations, for example, copy, move, splicing, actually adding or moving foreign objects into the scene. But all of those techniques are very advanced. You need a skilled person to implement those. On the other hand, cropping is the only method that requires no skill at all. It is very easy, it is very quick, it is very simple. So that is why I think it deserves a focused investigation. In this work, I'm focusing on the cropping only and no any other kinds of manipulations at all. Precisely because it is very easy to execute. So I hope that answers Shad's question. Since you try to reconstruct the input image onto a landscape aspect ratio, does it also handle the portrait inputs? It does not. This model is made for landscape photos only, but it could easily be extended. Like I could very easily train a second network that handles portrait inputs, right? There is just a finite set of aspect ratios. Most cameras have an aspect ratio of 1.5, which means the width is going to be 50% larger than the height. And this is why the input dataset consists exclusively of aspect ratio 1.5 photos, right? But again, it could easily be extended to portraits photos as well. Again, remember, this is just a proof of concept. There are a number of steps required to actually turn this into a complete software solution, but this is not really my job as a researcher. So then Abhijit Mahale asks, given the 60-70% accuracy, are there any other avenues to second result in order to prevent mischarging someone? I guess your question is in terms of, are there any other methods to detect crops? And the answer is usually not. Like if a photo looks cropped, for example, if a person's face is like cut in half, then a photo will look cropped, right? But oftentimes a bad actor will crop a photo in such a way such that it doesn't look cropped. For example, this one, it doesn't really look cropped, right? And same for this one, it doesn't look cropped. So I think it is important to be able to build a system that can withstand, that is robust against image content. Like we shouldn't just look at the semantics of the objects within the image, but also at the very subtle lens features that kind of reveal the location of every patch within the image. So I hope this kind of indirectly answers your question about seconding the results. Of course, this network isn't perfect. Like we would be living, it would be quite utopic to expect that this network performs excellently. But the point of my research with this is that we can tell real from fake better than chance. And that is already much more valuable than just random guessing. Can this idea be extended to detect anomalies in a video? That is again one of the possible future works that I've considered. So the answer is yes. This patch localization network doesn't have to be limited to images. You could very easily think of extension that kind of considers a spatial temporal patch and then tries to predict the location of a small video segment within the full video, right? So that is how you would be able to detect cropped videos, for example. How did you go about using resident aiding for unlabeled data? And the reason that I can use unlabeled data is because the proxy task that I'm solving here does not require any labels to begin with. All I need are the images themselves. The only thing I need to know is that they are full, uncropped, untampered images. And we can be quite sure most images on Flickr are untampered. I mean, they might be digitally retouched to kind of increase the brightness or contrast or whatever, but most of them are not been cropped. And then we can kind of extract patches ourselves. And then we know where we extracted every patch from, right? And then we can kind of assign that as a label for the network. So we extract patches at random locations. I'm pretending that I forgot where I extracted them from. I'm just asking the network to predict something. And then I'm gonna check that prediction against the actual location where I extracted it from. So that is how I kind of define this problem as a self-supervised learning task. So Rashida, hopefully this answers your question.
All right then, so do we have any other questions? Oh yeah, we have one more, I guess.
Yeah, so thank you for the question, Maxime. So the aspect ratio, there was only one aspect ratio in the dataset, which is an aspect ratio of 1.5. Most camera systems have an aspect ratio of 1.5, and that is why I selected 1.5. But this system could be extended to tackle other aspect ratios as well, right? Including portrait or widescreen aspect ratios. My best guess is that we simply need to retrain the network on a dataset that consists exclusively of, for example, 16 divided by 9 aspect ratio. There is just a finite set of aspect ratios out there in the world, right? It's not like a continuous thing. The most used aspect ratios are 1.33, 1.5, and 16 divided by 9. So hopefully that answers your question.
Alrighty. So, any other questions? In any case, almost at the top of the hour, but any of us have any other questions? You can also reach out to Basile, and sort of mail him the questions if you like. Basile, you can share your uni on the chat box so that if there are any questions, people can reach out to you. But this is incredibly helpful, I think, Basile. This is really amazing.
Thanks. I'm gonna also share my self-promotion and post my website on there. You can also contact me via there. So yeah, there you go. I believe a lot of participants are actually new to Columbia, so I'm also extending a very warm welcome to those who are joining the graduate engineering program next fall or next spring, depending on the coronavirus. Anyway, again, thank you for listening to my presentation.